Hello and welcome to your Naive Bayes lecture. So today we're going to talk a little bit about the conceptual and math of Naive Bayes. And Naive Bayes is a classification algorithm. So just like the other classification algorithms that we've been talking about, the Naive Bayes algorithm is looking to learn how to classify data points into different groups. So the Naive Bayes name basically tells you the two main things that you need to think about when thinking about the Naive Bayes algorithm. The first one is the Bayes part, and the Bayes part refers to Bayes' theorem, or sometimes called Bayes' rule, and I have the general form of it over here. We talked a little bit about Bayes' rule and conditional probabilities at the very beginning of our course. And in this specific context, when we're using it for classification, the way that we're going to apply it is we're looking for the probability of an outcome, which in this case is going to be like a category or a label, given the data. So essentially what we're saying is, what is the probability that our data point is in a certain category, given that we know the value of certain features that we have? And the way that we're going to calculate that is using Bayes' theorem, which says that the probability of a category given the data is equal to the probability of the data given the category. So how common is this combination of features in the category that we're looking at times the probability of that category. And these are both things that we can calculate from our data, as we'll see when we look at a concrete example. Now, this bottom part of Bayes' theorem, we're actually not going to use here, and I'll explain more on the next slide. So let's look at a concrete example. So say that I am trying to learn how to classify whether or not you had a heart attack. And the variables that I'm going to use to do that are, do you smoke, are you diabetic, and are you obese? Now, we can calculate the probability of having had a heart attack given that you are a smoker, you're diabetic, and you're obese. That is up here. We can also look at the probability that you didn't have a heart attack given that you're a smoker, diabetic, and obese. And essentially what we're going to do is we're going to calculate both of these, and then we're going to compare them, and whichever one is larger, that's the category we're going to classify you as. Now, if you look at these two formulas, you can see that the bottom part is the same in both of these formulas. So remember, we're just calculating these probabilities so that we can see which one is higher. Since they both have the same denominator, we're actually not going to calculate that at all. Saves us a lot of math. You're welcome. Because even if we ignore this denominator, whichever category is higher will still be higher even if we ignore the bottom part of our formula. So just to give you the official terms for what we use, we're going to say that the probability of our category given our data, write this out, is proportional to the probability of the data given the category times the probability of the category. So this formula ignores the denominator, which means less math for us, hooray. But remember that instead of being equal to the probability, it's now proportional, which essentially means whichever one was higher, whether it was for heart attack or not heart attack, that one will still be higher when we ignore the denominator. However, instead of being equal to the actual probability, it's only going to be proportional to it. And I'll just rewrite that over here. So then the probability of not having a heart attack, given that you're smoker, diabetic, and obese, is proportional to the probability of being a smoker, diabetic, and obese, given that you did not have a heart attack, times the probability of not having a heart attack. So when we go and try and calculate these variables or these values, we're basically now focusing right on these two parts, the numerator of our Bayes theorem. And we can get these values from our data. So the probability of being a smoker, being diabetic, and being obese, given that you have not had a heart attack, well, we can just look at our data and estimate that probability. all we do is look at how many people didn't have a heart attack and what proportion of those were smokers, diabetic, and obese. Similarly, we can calculate the probability of not having a heart attack by just looking at our data set and saying what proportion of the data points in our data did not have a heart attack. Okay, so that is the Bayes part of the naive Bayes algorithm. Let's look at the naive part of the naive Bayes algorithm. So given the example that we just looked at where we're trying to predict heart attacks based on whether you're a smoker, whether you're diabetic, and whether you're obese, we know in real life, based on just studies and medical research and etc., that smoking, being diabetic, and being obese, those three variables probably have some kind of relationship with each other. For instance, if you are diabetic, maybe you're more likely to be obese, or if you're a smoker, you're more likely to be diabetic, something like that. We know that there's probably relationships between those variables. Well, when we calculate the probability of being a smoker and being diabetic, we usually have to take those relationships into account. If you want to do this mathematically, the way we do this is if you want to calculate the probability of someone being a smoker and being diabetic, you have to calculate the probability of being a smoker and then multiply that by the probability of being diabetic, given that you're a smoker. Now, this is taking into account the dependence or the relationship between our variables. The naive part of the naive Bayes algorithm essentially says, ignore all that, pretend all your variables are independent, it'll be fine. And it actually turns out that our algorithm performs very well, even when we make this clearly false assumption that all of our variables given our categories are independent. So essentially what we're saying is, if you want to calculate the probability that someone is a smoker and that they're diabetic, pretend they're independent. Just say probability of smoker and diabetic equals the probability of smoker times the probability of being diabetic. So this assumption of independence, we know it's not true, but it turns out it doesn't affect the performance. So that's going to help us a lot with our computational efficiency because we don't have to calculate all of these conditional probabilities. Instead, we just calculate the probability of X and Y as the probability of X times the probability of Y. Saves us a lot of time and turns out not to affect the accuracy of our algorithm very much. Okay, so that is the naive part. So we've talked about the Bayes part, we've talked about the naive part. Let's look at an example. So this is a very classic type of example to look at with the naive Bayes algorithm, and that's because the naive Bayes algorithm actually has been used in spam filters, like for your email, with great success. Obviously, things are maybe a little more sophisticated now, but it's definitely a really good algorithm to do stuff like this. So we're going to look at a data set of spam and ham, aka real, emails. And this table is representing from our data set the probability of seeing these four words, Viagra, love, dollar, and buy, in an email. Now the top row over here is representing emails that are ham. So they're real emails. And so you can see, for instance, hopefully this makes a little sense, the probability of seeing the word Viagra in a ham email is only 3%, whereas the probability of seeing Viagra in a spam email is 32%. So we can see that there are different probabilities for seeing these four words given if you're spam or ham. Obviously, when we do these algorithms, we're probably going to look at more complicated and more features, but for the sake of this, doing the math by hand, I'm only going to look at these four. So say we have an email, and this email says, hello, I had a really great day. I would love to buy you lunch. Let me know. Okay, so this is an email and we have the text of the email and we want to classify it as either ham or spam. And we're going to do that based on the 4 variables that we're looking at here. So if we wanted to translate this email into data in the form that we have it here, what we would do is we would say yes or no, it has each of these 4 words. So it would be 0 because there is no mention of Viagra, thank goodness. It would be a 1 for love because it does mention the word love. It would be a 0 for dollar because it does not have the word dollar. And it would be a 1 for buy because it did have the word buy. So using these 4 features, we're going to calculate the probabilities of being ham versus being spam. Although remember, we're not going to calculate actual probabilities. We're going to calculate something that is proportional to the probability. And whichever email has the higher score is the category that we're going to guess this email is. Okay, let's calculate the probability that this email is a ham or a real email. So I'll write it down here, ham. So the first thing we have to do is calculate, and I'll write it up here maybe, the probability of 0, 1, 0, 1, and that's whether or not it has all those words, given that it's a ham email. So we're going to calculate that, and that is going to be, okay, for Viagra, the probability of not seeing the word Viagra in a ham email is 1 minus 0.03. And then times the probability of seeing the word love, which is 0.36. And remember, I'm looking at this top row over here because we're only right now looking at ham emails. Times the probability of not seeing the word dollar, and that's going to be 1 minus 0.02. Times the probability of seeing the word buy, which is 0.02. So now I've calculated this probability of seeing the data given that I'm in the ham category. And the last thing I'm going to do is I'm going to multiply by the probability of an email being a ham email in our database. Now we'll check this for assumption when we do the Python code, but I'll just let you know that half the emails in this data set are spam and half the emails are ham. So the probability of an email being a ham email is going to be 0.5. Okay, and once I've done all of that calculation, I'm going to get that the score that we're calculating, and remember, this isn't a probability, it's proportional to the probability, is going to be 0.00342216. Now, that's probably more decimal places than we need, but there you go, that's it. So now we can calculate the probability of the email being spam. And actually, let me just label that part. So this part... change back to pink. This is P ham. Okay. So now we have to calculate P0101 given that the email is spam. And because of our assumption of independence, remember, we're just multiplying all of these probabilities together. So we're looking at this row now, the one where it is the emails are spam. And the probability of not seeing the word Viagra is 1 minus 0.32, and then times the probability of seeing the word love, which is 0.05, times the probability of not seeing the word dollar, so that's 1 minus 0.83, times the probability of seeing the word buy, which is 0.774. And then I'm going to multiply by the probability of being a spam email. And in our data set, that's 50%. So times 0.5. And I'm going to get that once we do all the multiplication, this is equal to 0.0021386. Again, more decimal places than we need, but there you go. So now we've calculated the scores for each of our categories, ham and spam, and we need to choose whichever category is the highest. And remember, these scores are proportional to the probabilities, but they're not the actual probabilities themselves. However, ham is slightly higher in this case, so we would classify this email as a ham email because its score is higher than the spam email category. Okay, so hopefully that makes sense. We will go over another example when we look at it in the Python code, but that is all for the conceptual stuff. And hopefully now you understand what the naive Bayes algorithm does. All right, I will catch you next time.